Um, this is a recording covering the foundation of machine learning. So in this part, we're going to look at the machine learning concepts, what machine learning is, why data preparation matters, and how feature engineering transforms inputs. Then I'll cover the rest of the parts later. So what is machine learning? Machine learning is a branch of artificial intelligence where computers learn patterns from data rather than being explicitly programmed. So here we get a bunch of data and we feed it to a computer, and then it starts discovering patterns on its own and executes instructions without me, the developer, having to be there. Um, I use the metaphor for a Rolex store. Now, let's say you wanted the child to go buy for you breakfast, and you don't want to always be there telling the child that this is a Rolex stand. What you do, you find one good day, you send this child there to the roadside, and then you show him a lot of stores. Now, in those stores, you look for features like now a charcoal stove, um, the dough that is fly, ngano. Then chapatis, eggs, frying pans. Then you also show him how they dress, what they put on, the chapatis in the cupboard. So now, the next time you send this child and tell him, "Dad, buy for me a Rolex," this child would first go to the roadside, and now he will look for the clues. What does a Rolex stand now have? It has a charcoal stove, it has some chapati, it has eggs, it has a frying pan, and he also knows how the men dress. So you're not there, but you're getting what you want. Now, that is how also machine learning works. The programmer is not always there, but he gave this computer some data that's following, and through those patterns, it gets to learn what to do. Now, with machine learning, we collect historical data, then we train a model to discover patterns and apply that model to unseen data so it can make predictions. Why do we need machine learning? Now, the first thing is it can help us with complex tasks. hmm, Tasks that require a lot of rules to be written all the time in order to be accomplished. Then, the second thing is machine learning writes rules based on data and can continuously keep learning from them to solve the problem. For example, you can be there on YouTube, and let's say the developers want to recommend content. Rather than being there and having to program all the time, they can base on a colleague's data. For example, now Alex. Alex is a staunch Man U fan, and he only wants videos of football about Man U. He doesn't want Arsenal. So the algorithm keeps looking. What is he searching? What videos is he watching? And from that, it is able to learn that, Alex likes football, but for him, he only deals with Man U. It discovers those patterns within that data. Excuse me. Now, in machine learning, there are two types. The first one is supervised learning, and the second one is unsupervised learning. With supervised learning, here you're dealing with labeled data, and unsupervised learning, you're dealing with unlabeled data. Then within supervised learning, we have other methods. We have regression. So regression, you handle continuous data of a numerical data type. For example, can be dealing with height of students in inches. So this one is 5'4", this one is 5'8", this one is 5'10". So 5'10" means that it's taller than 5'4". Then 5'4" means it's shorter than 5'10". Then you have classification. With classification, you're dealing with categorical data that is exclusive from each other. It can be numeric or discrete and in a fixed range. So an example can be, let's say I was given names, Mpiji, Lira, Gulu, Kampala. Now, when you look at these ones, you can categorize and say, these are districts. Yes. Now, we also have unsupervised learning. What is unsupervised learning? Unsupervised learning, here you are dealing with a data set with no labels. So there's no labeling, eh? And it enables machine learning algorithms to learn based on no supervision. Machine learning algorithms learn from features to get more information through. Now we have clustering and anomaly detection. An example of clustering can be, let's say you entered a class, and you wanted to know people from Eastern region, Western region, Southern, yeah, Southern region, Eastern region, Western region, Central region, and the Northern region. You can base on the languages they speak. Now, if someone is good at Luganda, you can tell that this person most likely grew up from the Central region. Then, if someone is good in Lugisu, Lugisu, Lukwere, Lusoga, most likely this individual must be from the Eastern region. If someone is good at Nyankore, Chiga, Rutoro, this person must be from the Western region. So you are grouping them together basing on a similar characteristic, right? The languages. So that's where you have clusters. Then we have anomaly detection. Anomaly detection, you're detecting unusual occurrence of data instance in a data set. For instance, they use this a lot to detect fraud, whereby the bank can have the normal flow of transactions. Then that one day, they get a very unusual transaction. Like, something must be going on. So that's anomaly detection. And then we have data cleaning and feature scaling. Raw data can be messy, so you need to prepare it correctly before modeling. Data cleaning can involve removing noise. We talk about noise, we have duplicates, we have typos, then we can have missing values. And then feature scaling ensures that the inputs are comparable so the model doesn't overweight variables with larger numerics. For example, you can have age of a person and their salary. When you look at age, usually it's 3 digits, that's the maximum. Unless you are living before Christ, those people who used to go longer than that. Now in this era, you can't exceed 200. So you have age, and also you have salary. Salary, let's talk about now 7 figures, millions. So feature scaling helps us to deal with those variables such that they don't overweight each other. Here I wrote saying feature scaling helps with scaling numerical features, e.g., using min-max to 0 to 1. So variables like salary, which are in millions, don't dominate age years purely due to scale. So proper scaling yields fairer model training and faster convergence. Now, we have feature engineering. Feature engineering is the art of better inputs. Feature engineering can transform raw data into informative inputs that enable the model to see patterns. It is creative and often it determines proper model success. An example can be, assuming you went to the butcher. So when you're at the butcher there, they give you the meat. It's dirty, it's big. Now, for you bring that meat at home and you start cutting it into pieces. After cutting it into pieces, then you start adding spices. When you add the spices now, you fry it very well. Now, this is something can come out and can be delicious. It can be consumed by a person. But now, if you had it when it was raw, honestly speaking, to a human being, it wouldn't be feasible. Maybe to an animal, but it wouldn't be much feasible. So that process of chopping it, washing the pieces, adding some spices, that is now feature engineering. Until you're finding a way to transform it, to get better inputs so that by the time you fry, you come up with good stew. So here I gave an example of time-based features. You can have a timestamp, and from that timestamp, you can know what time of the day it is. Then you also have derived features. For example, you can want to find density, and you can base on the number of rooms plus the square footage, then you find the density. Yes, so in this part, I'll be going through the machine learning pipeline. Now, the first thing is to get the data. Then after getting the data, you perform the EDA. Then we prepare the data for machine learning. That's for the algorithm. We select a model, then we train that model. After training that model, then we fine tune it. And finally, we present our solution and launch it into a system. So models, let's talk about models. We have deterministic models and probabilistic models. Now, the ones that are deterministic, they deal with randomness, and they're very suitable when the prediction error is negligible. That means you can always ignore that error. And then we have probabilistic models. These ones, they deal with randomness in the data. So here, the prediction error is not negligible. Now, I recently covered the supervised learning and unsupervised learning models, but here I'm also going to go through them. So we say supervised learning. Here we deal with data that is labeled, and the goal is to predict a target. Then examples, we have regression, we have k-nearest neighbors, we have SVM, that is next slides. And we also have unsupervised learning, where we deal with unlabeled data. So we only take the input only, and the model keeps learning patterns that are hidden within that data. So we have PCA, that is principal component analysis. Then we have k-means, that's clustering. So there are some aspects of a machine learning model as well. The first one is a prediction model. That one, it predicts an outcome from X features, and the machine learning trains using the prediction. Then we have the cost function. The cost function compares the predicted value and the actual value. Then we have the optimizer. The optimizer's job is to simply optimize. So it finds ways of making the model much better. Now, we are going to look at k nearest neighbors and how they work. And I drafted 3 steps here. Step 1, we calculate the distance. So we measure the distance between the new point and every training point. That is Chilodian or Manhattan. Then step 2, we sort and find. So we rank distances and select the k closest neighbor. So for example, if we said k equals to 3, we would look amongst the 3 nearest points. Then we have the vote, the final one, which makes the verdict. So the predicted class is the majority label among the k nearest neighbors. So the majority vote decides the class. So what are the applications? Number one, use them for text mining, where you can sort emails and classify them. Then we have agriculture for identifying crop diseases from measurements made by comparing images to labeled data. Then we also have finance if you want to flag fraud transactions. Yeah, so we can look into historical data. And I also used in computer science competitions. Sorry, data science competitions. So what can we take away from this? The KNN is simple and very powerful. It also predicts by looking at the neighbor next to it. Though its main weakness is it has sensitivity to feature scaling and can have a slow prediction on large datasets. Now, decision trees. Decision trees, they are much clearer and easier to interpret. So you have a machine learning model that makes predictions by asking a series of simple questions. It splits the data into groups until it reaches the final answer that you want. So among it, we have categorical and numerical. So categorical can be, you have, let's say we give you Mukono, Gulu, Lira, Mubende. Now look at and look and say these are districts. I want to bring out something. But let's say I brought in districts in the central region. For example, I brought Mubende, Wakiso, Mukono, Kampala. So these are categorized under districts. So if I were to use a decision tree, it will be, is this district equal to X? Let's say I'm looking now for Kampala from Central. So I keep on branching, trying to find Kampala. Then you have numerical variables. Numerical variables, these ones, they measure measured values, such as rainfall millimeters, age, salary. So we can have a decision tree splitting them by asking the threshold question, like, is rainfall less than or equal to 20 millimeters, like that. So where do trees beat KNN? Now, the trees for them, they are good at handling with categorical and numerical data without normalization. So they split it into clear, simple regions, making models easy to understand and predict much faster. Yeah, so here is pruning. I talked about it because now these these forests, they face a very big challenge of overfitting. Overfitting is where the tree goes too deep, it memorizes the noise, so it can no longer differentiate. And what happens is it affects the model when it comes to predicting outcomes. So we can go and prune to reduce overfitting. Later, we're going to discover that there's another solution to solve this, where we use random forests. So what are the strengths? Number one, we said they're very easy to interpret. The second one is they can handle nonlinear data. And the third one is they can tolerate some missing values with minimal preprocessing. Weaknesses, overfitting, greedy splits, high variance, then sparse data issues in deep tree branches. So they are strong, but they have the biggest challenge of overfitting, which can be solved by pruning. Now, the next one, random forests. So random forests, there are many decision trees combined to improve accuracy. They have techniques like badging and boosting. So badging, you create multiple independent models using random subsets of data. Now you have your multiple models there. They're all having something to do and work on. Then later on, you combine the results, and then you can get an average for regression of a majority vote through classification. Then you have boosting. With boosting models here, you build models sequentially where each new model focuses on correcting the error of the previous one. Yes. So random forests can be able to do this. You can find a random forest having about 100 decision trees. So they're all working together. So by this, it helps to reduce on overfitting, a solution that, a challenge that decision trees can't work on. So we have support vector machines or SVM. What does it do? SVM finds a hyperplane that best separates classes. So I gave you a metaphor, the village. Rather than a small thin line, SVM builds a wide lane, which can be like a no man's land. So the wider the margin, the more confidence and better generalization to new data. So the way the model works is it prioritizes the boundary that maximizes the margin between groups for confident generalization. So support vectors are the data points closest to the decision boundary, and they are critical. So moving them can shift that hyperlane and can affect the model. Now, there's also cross-validation and data standardization. Data standardization here, you are dealing with features. So, for example, we spoke it the other side. You can have age and salary. So when you look at age, it's in millions. No, sorry, salary it's in millions, assuming for an employee. Then the age, it's in about the highest can be 3-digit figures. Yeah, I think that's the highest a person can reach now. Maybe it was during those times before Christ where someone would go up to 1,000 years. Now, you need to standardize these features so that you are able to come out with a better model. So we also look at it here. So SVM is distance-based. If features are on different scales, e.g. price in millions, EGX, or age from 1 to 100. Unscaled features dominate. Therefore, serialization comes in. Then we have SVM. Sorry, cross-validation. With cross-validation, here we use what we call K-folds. So SVM is sensitive to hyperparameters and it can split data into K-folds. So you can have like 5, then it trains on one fold and then tests on the remaining one, rotating until the fold is the test set. So you also have clustering. Clustering. So with clustering, it's a form of unsupervised learning, whereby you keep grouping data without labels. Now, let's say I came into a class and I wanted to know people from certain regions. Remember, I don't know their names. I don't know where they come from, but I can base on a characteristic like, for example, the language they speak. You find someone is good in Uganda, most likely this person comes from the what? Central region. And if someone is good at Lusoga, they can speak Rugwere, Rugisu. Most likely they come from the eastern region. Then if someone can speak Runyankore, Ruchiga, Rutoro, those languages, most likely this person comes from the west. Then vice versa. Now, that way, I can group them and I form clusters. And that is how clustering works. Strengths, number one, simple, fast, scales to large datasets. Very easy to implement and interpret, and always converges to the result. A problem is maybe sensitive outliers. Now I'm just imagining if I have individuals that are very fluent in both languages, now like Luganda and Nyankore, that person is an outlier. You find some individuals, they even know all from all regions. I doubt if that is possible. But yes, that is clustering for you. Then we have what we call PCA. PCA, in full, that is principal component analysis. This method reduces many variables into fewer while keeping most information. So I gave an analogy here of matoke. Imagine you at your home and you have your store and you come with a flashlight in the night. Can't touch the matoke. So it will give you like a projection of the shadow. But that's in 2D. So when you look at the spikes, can say, messing with these spikes from this shadow, this is what? This is Matoke. Just give an example. But now you have the 2D version. You have reduced the information from the 3D, whereby you could see in all the planes. So let me just read this. So I talked about the Matoke. So the shadow. The shadow it makes is 2D. So you lose one dimension. That's the 3D. But the shape is still clear. So PCA also works in the same way. It turns complex high-dimensional data into fewer dimensions while keeping the main patterns. Where is it applied? Number one, data visualization. Number two, it helps in noise reduction by removing variables that contribute little to the main patterns. Number three, preprocessing, produce concentrated inputs for heavier algorithms. And number four, it deals with image compression. Yes, this is the end. Thank you for listening.